Hello, everybody. Welcome back. Today's topic is Unit 7.13, which links the concepts of pH and solubility into one concept. So let's get started. All right, so the last few lessons in Unit 7, we have been looking a lot at the dissolution process, the dissolving process of slightly soluble salts. So we've been talking a lot about solubility and looking at KSP values, and we're going to bring in the concept of pH here. And the thing is that some salts, not all, but some salts, their solubility is affected by the pH of the environment. And as I said, we've been looking at a lot of slightly soluble salts lately, and many of the compounds that have hydroxide in them are slightly soluble or considered insoluble salts. For example, like iron 3 hydroxide is what our solubility rules would tell us is either slightly soluble or insoluble. It does not dissolve very much. However, this is an example of a salt whose solubility is affected by the pH of the environment. So I want you to imagine two different situations. Let's say that I'm dissolving this salt not in pure water, but in an environment, something that has a high pH, a solution that is very basic. Well, if you remember from some of the sort of foundations of acid-base chemistry, and we're going to talk a lot more about this in Unit 8, our next unit, if the pH is very high, it's very basic. What that essentially means is there is a large amount of hydroxide in that environment. So I want you to imagine if I am trying to dissolve this particular salt, iron 3 hydroxide, in an environment where there is already quite a bit of hydroxide, this is a common ion effect issue. Okay? Imagine it's like increasing the molarity of hydroxide ion. And what is that going to do? That is going to cause a shift in the reverse direction to consume some of this additional product and form more of the solid salt. So for this particular salt, if I try to dissolve it in a more basic environment, it's not going to dissolve as well. Its solubility will be less in a basic environment than it would be in pure water. Okay? That's very much like what we looked at in our last unit, the common ion effect. But what if it's the opposite? What if it is more of an acidic environment, which again, if you're remembering from your foundations of chemistry, means that there is lots of H+, or to be a little bit more formal, there's lots of this ion floating around. That's called hydronium. Okay, it's the ion that is essentially responsible for making things acidic. So in a low pH environment, there's going to be lots of hydronium, this guy, floating around. And you might say, well, okay, but that ion isn't a part of this salt. It shouldn't have any effect. But wait, remember back a few units. If you have a situation, an equilibrium situation, where you're adding more of something that isn't in your equilibrium reaction, remember that it's likely that this added thing must react with something in your equilibrium equation. And that's exactly what happens. And I'm going to write it out for you. What occurs is the hydroxide ion that is produced by the dissolving process ends up reacting with the hydronium to create water. Okay, and to balance it, we put a 2 there. HOH, same thing as H2O. All right, so so here's the net result. Every time I produce one of these hydroxide ions, it is going to then react with some of this hydronium ion. So essentially, guys, here's how I want you to think of it. It's like constantly pulling some of that hydroxide out, because every hydroxide that gets produced is then going to react with that hydronium. So what happens when you're constantly removing one of your products in equilibrium? Well, that's going to cause a shift in the forward direction this time to consume some of that solid salt and create more of the dissolved ion products. So what does that mean in terms of the solubility of this guy? It means, for this particular example, this salt, iron 3 hydroxide, will have a increased solubility if you try to dissolve it in an acidic environment. All right, so that's the way to think about this. Okay. Now, some salts, like I'll give you an example here, like calcium fluoride, you might say, okay, well, this is a salt that doesn't have hydroxide in it, so why are we talking about it? Well, this one is an example of a salt that has increased solubility in an acidic environment, and I'll show you why. Remember what we said. An acidic environment has lots of H3O+. That's called hydronium. Hydronium is not in this reaction, but I'll bet you that hydronium reacts with something on the product side, and it does. Okay, this is the reaction that occurs. Now, at this point in Unit 7, would we expect you to be able to predict that equation that's written in yellow there? Probably not. You're going to become a lot more familiar with these types of reactions in Unit 8. Okay. Essentially, the reason this reaction occurs is because HF is a weak acid, but as I said, we're going to talk a lot more about this next unit. But what I want you to know here and now is that because, let me go back. Because this F- is going to react with some of the hydronium that is floating around in the environment, that's going to lower its molarity. What is that going to do? That's going to cause a shift in the forward direction, causing some of the solid salt to dissolve, to be consumed, and the dissolved ion molarities to increase. Okay, that's going to cause calcium fluoride, this salt, to dissolve better, to have a higher solubility in this acidic environment. So let's look at a sample problem. Okay, we'll start off with a pretty simple one. So I'll read it out to you and then you pause the video and see if you can solve it. We've got an equilibrium reaction of a salt dissolving cadmium hydroxide. Will the molarity of cadmium ion, one of our products, be predicted to increase or decrease with the addition of hydroxide ion? All right, so I want you there's no math here, you're just predicting a concept here. All right, so pause the video, see if you can do it. All right. So hopefully you said that the molarity of the cadmium ion, which is on the product side, is going to decrease. All right, that would earn you 1 point of this hypothetical free response question. You've got to explain your reasoning. All right, with added hydroxide, the molarity of the products is going to increase. Okay, remember, adding more additional hydroxide is going to take us out of equilibrium, so we can talk about Q. Increasing the molarity of the products is going to cause Q to be greater than KSP. Remember back, guys, what happens when Q is greater than K? The reaction will shift in the reverse direction, consuming some of those dissolved ions and forming more solid cadmium hydroxide. And guys, they asked us about specifically what was going to happen to the molarity of cadmium ion if we are shifting so that the products are consumed. That means the cadmium molarity is going to decrease. Okay. All right, let's look at one more. This one's a little bit more complex. Okay, so I'm going to read it to you. If you want to pause, you can and try it on your own, or you can just listen to me talk through it. Same reaction, cadmium hydroxide. An experiment was performed to compare the solubility of cadmium hydroxide in pure deionized water and acidic water. So if you look at the pictures, container A has pure water, container B is acidic, and you can see there's lots of hydronium floating around in there. Which container would be predicted to have the highest molarity of cadmium ion? Again, they're asking us what's going to happen to the molarity of the cadmium ion, one of our products. So if you want to pause and try it on your own, cool. Otherwise, I'm going to talk through it. So the first thing I think about is, okay, H3O plus, that is not in this reaction. So I say to myself, but I bet that it's going to react with one of my products. And we looked at an example of that, if you'll recall. H3O plus reacts with OH minus to form water. That's going to essentially be removing OH minus from this situation. And think about what kind of a shift is that going to cause? It's going to cause a shift in the forward direction. So let's talk it out here. So which container would be predicted to have the highest molarity? That's going to be container B. Having that additional H3O plus, which is going to react with the OH minus, okay, that is going to be decreasing the molarity of the products. And to be specific, the OH minus, okay? If we're constantly taking OH minus away because it's reacting with H3O plus, that's going to cause a shift in the forward direction, which is going to consume some of that solid cadmium hydroxide and form more dissolved ions. So the point is, ladies and gentlemen, cadmium hydroxide, that solid salt, will dissolve more readily in container B than in container A. So container B is going to give me, again, we were focused specifically on this guy. Container B, I'm going to have a greater amount, a higher molarity of the cadmium ion, because there's going to be a shift in container B where there isn't in container A. Right. So those are some of the types of problems you could see. There's not going to be any calculations on pH and solubility. That's no longer on the AP exam. It's all just from a conceptual standpoint. So you need to be able to explain yourself. For those of you that do watch my videos, you will notice that there is a unit 7.14 in the College Board's list of units. It has to do with a concept called Gibbs free energy. I am actually not going to cover that little subunit, 7.14. I'm not going to cover that next. I'm going to save that for when we actually cover the concept of Gibbs free energy in Unit 9. So the concept that is covered in 7.14, if you're going in order with my videos, I'm going to hold off on that one and cover that concept later on in a unit, a subunit in topic number 9, Unit 9. All right. So that concludes Unit 7, at least for me it does. I hope that you have enjoyed this journey. I hope you've learned a little something today, and I look forward to seeing you in our next unit.